Welcome back. Um, let's start with this theorem. So here we have the external direct product of n groups here, and we are taking one element of that. So we have this n tuple g1 comma dot 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 comma gn. So this is an element of this external direct product, which means that g1 belongs to the group g1. G2 belongs to the group G2 here, and so on, and Gn belongs to the group Gn. So the natural question is, what is the order of this n tuple in this group? Well, the order of that is equal to the LCM, least common multiple, of the orders of the coordinates. So the order of an n tuple is the LCM of the order of the n tuples, order of the LCM of the order of the coordinates of the n tuple. Let me say that one more time. So the order of an n tuple is equal to the LCM of the orders of the coordinates of the n tuple. All right, here's an example. So in Z100, so this is a group under addition modulo 100. In this group, the order of 10 is 10, and in the group Z25, the order of 4 is 25. So 4 is the generator for Z25, and so notice that the LCM of this order 10 and the order 25, so the LCM of 10 and 25 is exactly 50, and so the element 10 comma 4, so the pair 10 comma 4, that's an element of Z100 cross Z25, and as an element of this external direct product, this has order 50, the LCM right here. In Z25, in the external direct product of Z25 and Z5, the order of 2 comma 1 would be 25, and the reason is the order of 2 in Z25 is 25, and the order of 1 is Z5 is 5, and the LCM of 25 and 5 is 25, and so the order of 2, 1 is 25. In the same external direct product of Z25 and Z5, the order of the element 5, 1 is actually 5, because the order of 5 in Z25 is 5, and the order of 1 in Z5 is 5 as well. So the LCM of 5 and 5 is 5, so the order of 5, 1 is 5. Okay, so here are a couple of exercises for you, and here are two more important results here. So if we are taking, let's say that the individual, let's say that the so here we have the external direct product of the two groups G and H, and let's say that the individual groups here are both cyclic, then when will it be the case that their external direct product is also cyclic? Well, the external direct product of two cyclic groups is cyclic if and only if the orders of the two groups are relatively prime. So G cross H is cyclic if and only if the order of G and the order of H are relatively prime. The external direct product of so here I have now n groups here. So we are taking the external direct product of n cyclic groups, and they are finite, and the external direct product is cyclic as well if and only if the orders of these groups are relatively prime pairwise. So the order of gi and the order of gj are relatively prime for any I not equal to j. So for the external direct product of cyclic groups to be cyclic, the component groups must have relatively prime orders. A consequence of this theorem is that if we take the external direct product of zn1, zn2, and dot dot dot, I'm missing z and k here, z and k at the end here, so this would be z and k. If we take that, then this would be identical to z, where with the modulus being the product of n1 up to nk, and that is the external direct product of zn1, zn2 up to znk is cyclic if and only if this modulus are relatively prime pairwise. So ni and nj are relatively prime for I not equal to j. Once again, I'm missing nk right here. Znk, sorry, znk should be here. So this is basically applying the previous theorem to the groups of this form. So here I'm going to state a couple of facts without any proofs here. So this is U2. So U is so Zm star. Another notation for Zm star is U of m. So U of 2 is basically Z2 star. U of 4 is Z4 star. So U of 2 is identical to this, has only one element. So this is like a trivial group here containing only the identity. U of 4 is identical to Z2. U of 2 to the n is identical to Z2, the direct external direct product, or sometimes we say external direct sum when the individual groups are abelian groups, and this is another symbol that is used for this case. So so U of 2 to the n is isomorphic to this group right here. So this is Z2. This is the external direct product, or you can say that the external direct sum, or just the direct sum of the groups Z2 and Z2 to the n minus 2. So the modulus here is 2 to the power n minus 2. This is for n greater than or equal to 3. For an odd prime number p, if p is an odd prime, then U of p to the n is identical to the cyclic group Z p to the n minus p to the n minus 1. So the modulus here is p to the n minus p to the n minus 1. So in particular, U of p to the n is going to be cyclic. If S and T are relatively prime, then U of ST is identical to U of S direct sum with the U of T, and the next theorem is basically a generalization of this first theorem. So if M is N1 times N2 times dot 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 Nk, where Ni and J are relatively prime for any I not equal to J, then U of M is identical to the external direct sum of U of N1 dot 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 up to U of Nk. I'm missing the direct sum notation right here. Okay, so this is it. Once again, the direct sum notation right here is used when the individual groups here are abelian groups. Okay, again, this is also this is just the external direct product of these two groups. Okay, so that's it. This is the end of this module.